Here's a real-world example that clarifies the difference between synchronous, asynchronous, and multi-threaded programming approaches. Imagine a restaurant kitchen where the goal is to prepare a simple dish. It could be a steak and a salad or an appetizer. Let's approach this task in 3 different ways. In the first kitchen, there is only one cook. The cook does everything by himself, from start to finish and one by one. He starts working on a dish, he prepares the whole plate, and moves on to the next one. He can do this because, while he likes to focus on his work, also his customers doesn't demand more from him. Every step is completed one task at a time, simple and efficient. In the second kitchen, we still have one cook, but now the cook has to multitask. That's, of course, for a reason. It's probably his customers is demanding more from him. He needs to provide more dishes at the same time. The key here is not doing multiple tasks at the same time. The key is managing multiple tasks at the same time by breaking them down into smaller chunks. So imagine he might be grilling a steak and preparing a salad. He puts the steak on the grill. While the steak is cooking, he goes, chops some vegetables for the salad. He goes back to the steak, checks it, maybe turns it a little bit, then chops the salad again, back and forth. Right? These little steps, little tasks, are still executed sequentially, but the cook switches between them. And here's an important point. This type of multitasking is only possible when there's something else doing work for you. In our examples, that is the grill. Right? Because the grill is cooking the steak already, the cook can put his focus on something else. But he should not forget about the steak, because otherwise it will be bad. Then comes the third kitchen. Right? We have multiple cooks working together. One of them can grill the steak, the other one can work on the salad. We might even have multiple cooks grilling steaks all at the same time, but there's a catch. How your kitchen is designed is also important. It should provide enough resources for multiple people to work at the same time. For example, if there's only one grill in the kitchen, it doesn't matter how many cooks you have, only one of them can work at a time. So this limits the efficiency of your kitchen. But if you have multiple grills, then multiple people can all grill steak simultaneously, which is nice. Right? The key difference here is tasks are actually executed at the same time because we have more resources. So 3 different approaches, but which one is really better? Right? Which one provides better quality, or which one provides better throughput? So which direction should we go? Now imagine this restaurant is your Python application. Like the case where one grill limits multiple cooks, also we have the infamous GIL in Python, the global interpreter lock, also limits the multi-threading capabilities of Python interpreter. Right? Because in the traditional Python, there is only one thread can execute Python bytecodes at a time because of the GIL. And of course, GIL is there for a reason. But this is also changing nowadays. With the new version of Python, there's an option to allow free threading without the GIL. And with this change, it's like Python's kitchen just hired more cooks and added more grills, so things can finally happen at the same time. But the question is, do we still need async? Do we still need our efficient multitasking cook? Well, hello everyone. My name is Samet Yaslan. Today, we will explore the choice between multithreading and async, and how this choice is influenced by the removal of the GIL. So, short introduction of myself. My name is Samet. I've been working at a company called Optiver since 2014, with a strong focus on clean, well-tested, and simple code bases. I'm also part of Optiver's Python standards group, where we try to modernize our Python code bases and also make best practices well known to other teams. There's a QR code if you want to add me in LinkedIn. You can do that. Also, a short introduction of the company. So Optiver is a technology-driven trading firm where we use technology to provide liquidity to the financial markets around the world, to trade on financial markets around the world. We have nearly 2,000 employees, like 50 nationalities, all working to solve complex problems by using technology. Also, a quick side note, the pictures I've just shown you was from our actual kitchen in the Amsterdam office. Really great people. Just want to thank them from here, like providing us great food every day. But if you want to know more about what we do or how we use Python at Optiver to do what we do, feel free to reach out to me after the talk. Happy to talk. So let's go back to the talk. Why are we even discussing this? As I already mentioned, there is a change that is happening these days. With Python 3.13, there is an experimental and optional way to disable the GIL. Right? The C Python is introducing this compile time flag, and if you compile your interpreter with that flag, then you can have a Python version without the GIL. And that's already actually available to download if you want to try it. So this free trading execution enables threads to run at the same time across multiple CPUs, which is something new for Python, right? Allowing complete utilization of the available processing power using threads. So for decades, Python has been limited by the GIL in that sense. Like you should have used multiprocessing, but you cannot use multi-threading. But now you can. Like we can finally have free threading in Python, where multiple threads can execute Python bytecodes at the same time. But what does this mean for async? Well, let's find out. Right, let's start by breaking down these 3 different approaches, beginning with the synchronous programming. So what is synchronous programming, really? I think in this model, the tasks are executed one at a time, from start to finish, in a strict and sequential order. The program basically waits for each task to complete before moving on to the next one. And this simplicity makes it actually very nice because the code is much readable, the code is much easy to understand, it's clean, easy to test, and also easy to debug. So if your program is, for example, a batch process or a command line tool which gets an input and provides an output in a reasonable amount of time, this is a nice alternative. But if your program needs to do a lot of I/O and needs to wait during that I/O, this might be still OK or might not be OK, because your entire program will remain blocked. So, but what about async? So async actually brings a nice solution to this problem. It's a nice model for handling I/O-bound tasks more effectively. So the focus is here on multitasking, but not parallelism. It's not about doing things at the same time. It's about breaking things down into smaller chunks, and those smaller chunks are still executed sequentially, most likely on a single thread. But then it creates the illusion of concurrency. Your program is sort of more responsive. Like, for example, if you have a user interface, this is a nice alternative because you will get responses from your program. But it actually doesn't make it any faster or powerful because in the end, most likely you are still on one CPU, one core, one thread, and that is the most you can get from that CPU anyway. So also there's some downsides with the async, like the learning curve is a bit more steep because it's a bit more difficult to grasp what is actually going on under the hood. And debugging can be tricky in that sense. But despite these challenges, async can be a nice alternative, depending on your case, especially if you have a user interface or a web server, for example, where there is a lot of I/O going on, and there is something else doing work for you. Like in the I/O example, there is probably the network interface doing work for you, and it's OK to do something else when the network exchange is happening. Finally, let's talk about multithreading, a model designed to handle CPU-bound tasks at scale. So multithreading focuses on executing things at the same time because you get to utilize more CPU cores. Of course, with the standard Python and with the GIL, there is a limitation because the GIL only allows you to execute one Python code at a time. It doesn't matter how many threads you have. And it's not doing this because it's evil or something. It's doing it for a reason. GIL is a really nice way to protect the inner state of the CPython interpreter in a simple and effective way, which makes things easier for CPython to work. But it comes with a cost, that it makes it impossible to run Python code, Python bytecodes on multiple threads. Good news is, now this is changing. Like there's an effective way to remove the GIL without compromising the inner state, without compromising the performance too much. And this allows threads to truly run on multiple cores, right? And this change is started with 3.13 already. Like 3.13 is available, is a separate build as 3.13t, where you can download and try the free-threaded version. It is still called sort of experimental in 3.13. In 3.14, it's not going to be experimental anymore. It means there is more support and more trust in this functionality. So developers can actually now choose to use a free-threaded version if they want. But is it for free? Of course not. A lot of existing libraries are actually developed where there was still GIL. And the GIL was providing sort of a mutex functionality at the background, and that was creating some safety for those libraries. And now without the GIL, those libraries has to adapt to the new version. And there is also, of course, lots of progress have been made already, like especially for the machine learning ecosystem. A lot of the well-known libraries, they provided new versions, newer packages, where they support the 3.13t, the free-threading version. So despite all these challenges, multi-threading without the GIL is a major step forward and provides powerful performance improvements for the CPython interpreter. So there are 3 different models. But how do you choose? Like, what is the right model for your problem? Well, when one CPU is enough for you, and when you don't need responsiveness doesn't matter, I think the simplest thing you can do is just to use async. Like, if you are preparing a simple meal with no interruptions, there is no need to overcomplicate things. You can just do one thing at a time and then have a really nice final product. It is straightforward, easy to understand, and perfectly suited for tasks where there's simple input, simple output, and reasonable amount of time for you to process that. You should consider using synchronous programming for tasks that can be executed one after another. Of course, when this execution is happening, your program will just do that and nothing else. But it can still produce a lot of performance because you have the full potential of one CPU core on one thread. So this, as I said, this can just be fine for batch processes or even for I/O when the responsiveness is not a problem. It's a solid choice, simple and straightforward. But it quickly becomes a bottleneck when your program needs to respond. Like when you need high responsiveness, like a user interface. And that might be a good place to think about async, right? When one CPU is still enough for you, but responsiveness matters, right? If you are cooking a meal that involves a lot of multitasking, right? You need to do one thing and then go chop some vegetables and boil it. Like you shift the one pot to another pot. You look at the grill, turn the steak. Right? There's a lot of things you are doing at the same time, and you have to do that to have a final product. I think a burger is a really nice example. Like you prepare the bun, but in the meantime, you're grilling your burger, and you put some sauce, a little bit of onions, but then all this has to happen sort of simultaneously. You don't need multiple people to do all of them at the same time. You can do that all by yourself, but you need to switch between those tasks. So similar to async, right? It basically excels when your application does a lot of I/O, for example, while you wait for the network to respond to your query, then you can do something else. You can even have a web server on one CPU core if the tasks that you're executing is not so processor heavy. You can just switch between those connections all the time. As long as you are responsive enough on one thread, you'll be fine. So async can allow you to handle thousands of connections in one thread, right? With one CPU even. However, if your goal is to generate processing power, then that doesn't work because you are in the end bounded by one CPU and whatever that CPU core provides to you, because you are most likely on still one thread. That brings the next one, of course, when to use free threading. Right? When one CPU core isn't enough for you and you don't have GIL, then free threading becomes an option in Python. Like if you have sort of a dish that requires a lot of preparation, a lot of complexity, a lot of work, and just one person is not enough to do all that, you need multiple cooks working all together at the same time, right? That is the point where you need multi-threading. When your workload needs more processing power, more CPU. So heavy computations, for example, or mathematical calculations, those are good examples. And you can now leverage the free-threaded, GIL-free version of CPython for real multi-threading. Things can truly run at the same time. So we have multiple cooks and multiple grills in Python Kitchen, and they work in harmony without blocking each other. So before you leave, I want you to remember a few things. Synchronous programming is likely our default, simple and effective. You can use async when responsiveness matters, and one CPU core is still enough for you. When you need multiple cores, and when you need to run Python code on multiple cores, now you can use the free-threaded version of CPython. Python without the GIL is a fantastic new tool, but it doesn't really replace async. It just gives us more options. Thank you.
OK, we've got a few minutes for questions. Any questions? Just raise your hand. I'll come to you. Oh, excellent. I'll sort of come to you.
Yeah. Thank you very much for the nice talk. Could you put the multiple interpreters feature from 3.14 into the picture? When would I use multiple interpreters?
Do you mean sub-interpreters?
Sorry?
Do you mean sub-interpreters?
Yeah. I read here in 3.14 there will be concurrent interpreters.
Yes.
Yeah.
Yes. It's also a little bit available in 3.13 already. Indeed, that wasn't part of my talk, but basically we are getting two different options in the upcoming Python versions. One is what I talked about, the free threading, and the other one is another approach, basically the ability to run multiple interpreters in one process. It's called sub-interpreters. It's also a very nice approach. It has its ups and downs, pros and cons, obviously. But it's basically something that has been there all the time in the CPython, but that was never exposed to the Python. Like it was only available from the C interface and then never from the Python interface. Like you weren't able to write Python codes until 3.13 to benefit from that. And recently also there was a change in CPython. So in the maybe 3.10 or so, the global interpreter lock was still limiting those sub-interpreters. So they weren't able to run Python bytecodes at the same time because the whole process had one global interpreter lock. With 3.13 or 3.12, that has changed. Now we have little local interpreter locks for every interpreter in one process. If you are able to spin up multiple interpreters in the same process, then you can actually execute Python bytecodes at the same time. And that is indeed a second approach that's also coming up. Depending on your use case, could be a nice alternative.
Thank you. Hello, thank you for the talk. You said that the library ecosystem needs to adjust to the free threading, but I'm not really sure why that's, what's the difference? Because if you, when you had the GIL, you still needed to take care to lock the conflicting sections of your code. You couldn't just let the GIL take care of everything. So what's the difference? What do these libraries need to do to adjust to non-GIL threading opposed to GIL threading?
So the question is, why does the libraries need to adapt basically to the free threading? I think the answer could be grouped in two. One is with the free threading version, the C interface, C API of C Python is also changing, and every library, every C extension that integrates with the C API has to adapt to that change. And that's like, it's not a minor change, it's quite major, it requires some work. So that is one. And the second part is some Python libraries, they basically relied on GIL for multi-threading instead of doing what you just said, instead of having local locks. And that just worked because the GIL was there and protecting them, maybe without them knowing or knowing, doesn't matter. But now, when it's not there, those libraries have to adapt.
Hi, thank you. So you talked about thread pool executor, the new sub-interpreters, from what I understood. Can you also talk about where do process pool executors fall into this category so I understand it better?
So
the process pool executor.
You mean like multiprocessing, basically?
Yeah, I suppose.
Yeah, that was always an option in Python. You always had the option to have multiple processes and achieving concurrency, doing things on multiple cores at the same time, using that. And that will still be there. I think the difference between those three things is, with multiprocessing, your logic is far apart from each other, and to communicate between them is more difficult. With sub-interpreters, it's coming a little bit more closer, so it makes it easier to communicate between them more faster. But with multi-threading, then they really start living in the same kitchen, right? So for multiprocessing, is imagine like I have a restaurant here and there's another restaurant, and then like I prepare one thing, he prepares one thing, but we need to coordinate very well to do them at the same time. The sub-interpreters is like there is one kitchen in the same building, another in the next room, and then they can give things from the window maybe, but still requires some effort. Multi-threading, free threading is like they are really in the same environment and doing things all at the same time.
Thank you for the analogy.
Other questions? Oh, yeah.
Okay, thank you for the presentation. Just out of curiosity, is it possible or does it make sense to use async programming with multi-threading programming with the GIL at the same time? For example, like to run asynchronous code with a multiple thread to multiply the responsiveness of async?
I think it's possible, but traditionally, normally most people just use async on one core because async gives you the benefit of having concurrency without having to deal with the multi-threading. But if you have such a good reason to do so, perhaps you can, yeah.
Thank you.
Other questions? Just look around quickly. All right. Thanks so much, Samet, for a great talk.